Hello and welcome back. We are going to switch to something completely new for now. We've been talking about all sorts of things in chemistry, and what we talk about is this atom, this molecule, these relatively large things doing stuff, interacting with other things, we're weighing them, we're doing all kinds of stuff. But what we're going to go to next is what happens to individual atoms. So we're talking about a single atom at a time for now, when it's not happy. We know that atoms and molecules, they get together in order to be happy, form ionic bonds, covalent bonds, in order to either get electrons or to do whatever it is to look like noble gases. But what if this an atom all by itself is unhappy? And in this case, what unhappy means is if its nucleus, the little tiny part inside there, if its nucleus is unhappy, what are we going to do about it? So the first thing we're going to do is we're going to look at some periodic trends, and we're just going to make a list of some elements on the periodic table. So we've got our element, the average atomic mass, the number of protons, and the most common number of neutrons. And we'll talk in just a second about how we figure that out. We start at the very beginning of the periodic table. We have hydrogen. Its average atomic mass, we're going to round to whole numbers here, is 1 AMU, 1 gram per mole. We know that hydrogen has 1 proton. Now, most often, how many neutrons does hydrogen have? Well, if you remember back a while ago, we learned that a proton weighs 1 AMU, and a neutron weighs 1 AMU. So hydrogen already has a proton, so that proton weighs 1 AMU, and the average hydrogen atom weighs 1 AMU. And so guess what? The average hydrogen atom, the average hydrogen atom has 0 neutrons because that proton already takes care of the average atomic mass. But if we move over to helium, the average atomic mass there is 4. The number of protons is 2. Well, we've got things that may add up to a mass of 2 AMU, but we need to add up to a mass of 4 AMU. So the most common for helium must be 2 neutrons. And so we get 2 protons and 2 neutrons is the most common helium atom out there. Keep moving along our periodic table. We get lithium. Its average mass is about 6.9 or so. It's got 3 protons, which means it must have 4 neutrons. 3 plus 4 is 7. And so we can keep doing this. We're not going to do the whole periodic table. Let's skip up to boron. It's got a mass of around 11. It's got 5 protons, and that must mean it's got 6 neutrons. And our last one we'll do calcium. It's got a mass of 40 AMU and 20 protons and therefore 20 neutrons. And so we have this little table here. And what does this table tell us? These are, again, the most common isotopes that exist for these elements. And if you look at these other than hydrogen, you'll find that the most common isotopes generally have about the same number of neutrons as they do protons. In some cases, maybe a little bit more, 1 more in these cases. In some of the bigger atoms, it's a few more than 1 more. But roughly same number of protons as neutrons, and those are the happy ones, and that's why they exist naturally. We don't find calcium with 47 neutrons because it's just not happy and it won't exist that way. So what happens when we get atoms that have not the right number of neutrons, either too many neutrons or not enough neutrons, and they're just not happy? What are they going to do? Well, it turns out what they do is they undergo nuclear radioactive decay. Sounds very fancy, but all it means is that the nucleus, the little tiny thing in the middle, will actually fall apart into pieces in order to become a little more stable, in order to become a little bit more like roughly equal protons and neutrons. Now for this class, you won't need to be able to predict that and be like, oh, I think this one will do this, I think this one will do that, but I do want you to understand these reactions. And so what we're going to do is we're going to look at the different ways it can fall apart and make sure we can figure out how to balance those so that we don't lose protons, we don't lose neutrons, because we're not going to be doing any of that. So we're going to balance nuclear reactions, but we're not going to predict nuclear reactions. So what are different ways that these unstable atoms could fall apart? Like if we had calcium with 27 neutrons, it wouldn't be stable. How would it fall apart? First kind is an alpha particle. Now alpha, the Greek letter alpha, looks just kind of like a little fish right here. Some people will draw it a little fancier with kind of like curvies on the alpha, but I don't have good handwriting, so I just make a very little simple fish. What is an alpha particle? An alpha particle is a helium. It's actually a helium nucleus emitted by the nucleus of an unstable atom. So an atom that has not happiness will actually spontaneously, poof, make a helium atom fly off. Now, what kind of things are going to do that? Well, a very common one is uranium-238. Uranium-238. You remember our notation here. This number in the top left is called the mass number. It's the number of protons plus the number of neutrons. This number down here is called the atomic number. It is equal to the number of protons is what we've done so far, but we'll see that change in just a moment. And then obviously U is just the symbol for uranium. But what uranium can do, uranium-238 specifically, is it's unstable. It's not happy. It doesn't have the right balance of neutrons and protons. And so it will spontaneously fall apart, which means there's nothing else on the left-hand side of that reaction. There's nothing reacting with uranium. It's just sitting there and all of a sudden decides to go poof. It's kind of like a popcorn kernel. You're sitting there watching it and all of a sudden, poof, it turns into popcorn. Uranium will do that. Now, what does it break apart into? Well, it breaks apart into an alpha particle, 4,2He. And what else? How are we going to figure out what else it breaks apart into? Well, it turns out when we're balancing these nuclear reactions, atoms falling apart, their nucleus falling apart, the two things we want to balance are mass number and atomic number. And that's all we need to do in order to balance these. And so what we're going to do is we're going to make essentially an equation out of it. So on top up here, we've got a mass number of 238. This arrow is going to be our equals sign. And we've got a mass number of 4 for our helium plus something, right? And so now we've just got a little algebra equation. 238 equals 4 plus what? Well, it's equal to 4 plus 234. So we know that the mass number of our little question mark here is 234. We're going to do the same at the bottom for our atomic number. We get 92 is equal to 2 plus our new atomic number. And of course, that makes y equal to 90. So now we have the mass number and the atomic number. What we need to do is cross-reference on our periodic table. So you look over here on the periodic table, and you're going to try to find what has the atomic number of 90. And if you went ahead and go to do that, what you would find is that it is good old thorium, named after the god of thunder. So we don't have a question mark there anymore. We just figured out that uranium-238 undergoes decay by alpha particle, which is a helium, forming your thorium-234. And that's how we could say that out loud. Now, another thing that I want to point out is this little thing here, 42He. There's a bunch of different ways that people will write that. Some people will write 42He. You'll see some people, not too often, just write He. But quite often you will also see people just write the symbol alpha, or they will write 42 alpha. There is no difference whatsoever between these 4 ways of writing that possible product. And so you have to be familiar with all 4 of those. Certainly, this one is not too common, so you're not going to see it very often, but the other 3, very, very common, and it just depends on what the author likes and what the author's trying to get across. So be familiar with that, and you'll see that in some of our examples coming up. But again, how we balance these things is we balance mass number and we balance atomic number. So that's one way that atoms can fall apart if they're not happy. What's another way? Well, if you know your Greek alphabet, what comes after alpha is beta. And so we have our next type of radioactivity, which is a beta particle. Now, what's a beta? it looks kind of like a B, but what you want to do is put a little tail on him right there. And again, people who have great handwriting have fancier ways of writing that, but I just write a B with a tail. And what is a beta particle? A beta particle is an electron emitted from the nucleus. And that sounds all well and good until you think back and what did we learn about electrons and where they are? Are electrons in the nucleus? No, remember? What's in the nucleus? Protons and neutrons are in the nucleus, and then the electrons are really, really, really far out. Remember, halfway to the moon if you scaled up? Wow, really far away. So how can I say that there's this thing called a beta particle, which is an electron emitted from a nucleus? Where is that electron coming from? Like, does it like grab one from way out there and get it and then release it, kind of like a rubber band, and then it flings off? No, it turns out that even inside the nucleus, there are electrons. Where are they coming from? Here's the crazy part, folks. They're coming from the neutrons. Because it turns out a neutron isn't just a neutron. It's a proton and an electron squished together. And when you squish them together, the proton is positive, the electron is negative, and when you squish them together just the right way, you get a neutron. Crazy. And what happens is that neutron, like we're not even talking about the nucleus breaking apart, we're talking about a neutron breaking apart. It breaks apart into a proton and an electron. That electron flies away and it leaves the proton behind. So what kind of thing undergoes this type of reaction? One that we'll talk about later that you might have heard is called carbon-14, used for carbon dating. And again, it's decaying all by itself, so there's nothing else on the left-hand side of our reaction arrow. And it falls apart into a beta particle. So I'm going to use my B there. And what else? And if you remember from our last slide, how are we going to balance this? We're going to balance mass number and atomic number. So we do that. 14 is equal to, we didn't put anything in the mass number there for beta, did we? What would be the mass number of beta? Well, mass number is number of protons plus number of neutrons. And a beta particle is an electron. Remember, electrons are tiny, right? They're 1,000 times smaller than a proton and 1,000 times smaller than a neutron. So how many protons are in a little tiny electron? None. How many neutrons are in a little tiny electron? None. So you get 0 plus 0 is equal to 0. And in fact, that is the mass number of our beta particle, is 0. Now, atomic number. We always said, hey, that's the number of protons, and so you might be tempted to put a 0 there as well. And that's not quite true. Yes, when we're talking about atoms, the atomic number is the number of protons. But when we're talking about nuclear radioactive particles, that number on the bottom is actually the charge of the particle. And the charge on an electron, we know, is -1. And so a beta has a mass number of 0 and an atomic number of -1. But that gets us what we want now, because now we can balance that out. 14 is equal to 0 plus x. That makes it pretty easy, 14. And then on the bottom, we can do 6 is equal to -1 plus y. This one's a little trickier, so you want to think about that for a second. Now you can actually do the algebra and add or subtract -1 from both sides, but what you end up with is 7, right? 7 plus -1 is 6. And so 14(7), you're going to cross-reference onto your periodic table, find element number 7 over there. If you find element number 7, you will see that it is nitrogen. And so what we can say out loud is carbon-14 undergoes decay by emission of a beta particle to form nitrogen-14. Just like in the case of the alpha particle, there's a bunch of different ways of talking about beta. Some people will write 0 minus 1b. Some people will just write the beta all by itself, and you have to know that it's 0 minus 1. And some people will write 0 minus 1e, And even you'll see people write 0 minus 1 E minus. And that doesn't mean there's 2 minus charges. They're just telling you the minus twice, just to make sure that you really see it. So those are 4 different ways of writing the beta particle. You should be familiar with all of them and understand that they are entirely equivalent. There's no difference in meaning between any of those. So we now have alpha, beta. If you know your Greek alphabet, the next one is gamma, which is not what we're going to talk about next. We will talk about gamma towards the end, but it's a little bit different. So what we're going to talk about next is a positron. What is a positron? Positron. Posit sounds like positive, doesn't it? Tron. Isn't that the ending from electron? So a positron is a positive electron? No, electrons are negative, right? What are we talking about? This is crazy stuff. And yes, it's true. This is crazy stuff. Nuclear chemistry is like the craziest thing you can deal with in chemistry. A positron is a positive electron. Where are we getting positive electrons from? Electrons are negative. It's like one of the fundamental things we've been talking about. Electrons do all the chemistry for us, and they're negative, and they repel each other, and that's what Vesper is. And where are you getting a positive electron from? Especially in a nucleus. Whoa. Wow, where do you get the positive electron from? And this is crazy. What's positive in the nucleus? Protons. And it turns out a proton isn't a proton. A proton is a positron squished together with a neutron. Whoa. And so what happens is one of the protons in that atom falls apart, emitting a positron and leaving behind a neutron. If you want to get really crazy, you remember our last slide, what was a neutron? A neutron was a proton plus an electron. But what's a proton? A proton is a positron and a neutron. And I don't know where all that ends. Luckily, as chemists, we tend to stop right here, and we don't delve down that what happens if kind of field. That's for the physicists. Good job, guys. Alrighty. So it falls apart into a positron and a neutron. Now, what chemical in the world would possibly do that? And you think, I don't know, it's got to be one of those exotic ones. And it's not. There's things that do it that you might deal with on a daily basis. Now, I'm going to tell you might deal with aluminum on a daily basis, but you probably don't deal with any aluminum-24 isotopes on a daily basis. The isotopes that are in your sheet of aluminum foil or your can of aluminum are not aluminum-24. Okay, aluminum, it is number 13 on the periodic table. It's undergoing decay, so there's nothing else on the left-hand side of our arrow. A positron doesn't have its own little symbol. We just use an E for it because it's the same mass as an electron. It's just got a positive charge. Now, if you remember in the last slide, we talked about beta particles having no mass number, 0 mass number. The same is true for a positron because it's got no protons, it's got no neutrons. But here we're going to use a +1 for the charge. And I highly encourage you when you are doing this, I highly encourage you to put the +1 in front of there because people do use the 0 minus 1 to indicate a beta particle. And it's really nice to have that positive sign to say, no, really, I mean positive. I didn't actually just forget to write a sign there. So I encourage you to use that 0 + 1e when you're writing these things down. And then we got to figure out what else is made there. And we do our mass number and atomic number balancing. 24 equals 0 plus what? Yeah, 24. And 13 is equal to 1 plus what? Right, 12. And so 24, 12, we've looked at the 12th element on the periodic table, which is magnesium. And so we say aluminum 24 undergoes positron decay to form magnesium 24. So you remember when we talk about these atomic symbols out loud, these isotopic symbols out loud, we just say the element name aluminum, and we say the mass number of 24. So we call it aluminum 24. So crazy, but neat that these little subatomic particles that we thought were really the fundamental things that made our universe are not, because they can be broken down too. A couple more to deal with. Type of radioactivity, proton emission. This one, hopefully the name kind of tells you what's going on. Proton emission means a proton is emitted. A proton separates out from the nucleus and flies off into infinity and beyond. So what thing would undergo proton emission? 15171, and if you look that up, that's the lovely element lutetium. And you know, I'm not 100% sure if I pronounced that correctly, so internet, please don't make fun of me. Thanks. All right, so lutetium 151 undergoes proton emission, and what we do for proton emission is we just put a P there. Now, what are we going to put as the mass number for a proton? How many protons in a proton? 1. How many neutrons in a proton? None. And so we're going to put a sum total of 1 there. What's the charge on a proton? It is +1, and so you can just put a 1,1p there. Some people will just write the p all by itself, but you need to know that it's a 1,1p. Then what's left over? 151 is equal to 1 plus 150, and so we can put 150 here as our mass number. And then 71 is equal to 1 plus 70. And so we can put 70 here as our atomic number. And that's one of my favorite elements just because it's a funny name, ytterbium. Okay. So ytterbium. So lutetium 151 undergoes proton emission, to form ytterbium 150. The reason I say this is less common is because as far as we know, it only occurs in artificial isotopes. Now, what's an artificial isotope? It's ones that we've made in the lab down here on Earth in these particle accelerators. We can do these things, fancy things, and make new elements. It's amazing. But we've only observed proton emission in those types of elements, not in nature so much. And so we call it a less common one, but it still exists. And then if there's proton emission, there is also neutron emission. Again, less common, not seen often in nature. And what undergoes neutron emission is its mass number 249 CF, and it has an atomic number of 98. And if you look up what CF, it's californium. And so you can guess maybe where it was discovered in Vermont, right? It was discovered in California. The Vermont people aren't just being nice to us. It was discovered in California. It's undergoing neutron emission. We just use an N for that. How many protons in a neutron? None. How many neutrons in a neutron? 1. And it's got no charge, and so we put a 0 there. So 1, 0, N. And then what's left over? We get 249 is equal to 1 plus something. That's going to be 248. And we get 98 is equal to 0 plus something. And so we still get 98. And neutron emission does not change the identity of our atom because it's only a neutron being emitted. It's not changing any protons around. Because if you remember, protons are the only things that tell us what kind of atom we have. So there we go, neutron emission. And those are 5 different types of physical particles that we're going to be talking about. Alpha, beta, positron, neutron emission, and proton emission. Those are the 5 types of decay particles. And we should be able to balance reactions. In our next video, we'll have some practice doing that. But the last one we're going to talk about is the gamma, alpha, beta, gamma. And what is that? It looks like a fish swimming down. And again, people with better handwriting make them a little fancier, but I just make a little fish swimming down. But the thing about the alpha particle is it's energy only. And it just says that when these types of nuclear reactions happen, when these protons are emitted, when these positrons are emitted, they emit a lot of energy. And that energy is usually so energetic that we talk about the energy, the light coming off, being given off as gamma particles. You remember gamma was the very, very high end of the energy spectrum in the electromagnetic spectrum. And these ones, right, no mass number, no atomic number, so you'll see people write it like that. They don't change how you balance the reaction. They're just there to make sure that people know that there's a lot of energy coming out of this reaction. And so you'll see that occurring in some reactions, but it doesn't change how we balance things. All right, one question before we go. Which particle of radiation is the lightest? Is it a proton, a neutron, an alpha particle, or a beta particle? So pause for a second, think about that answer. And what did you come up with? Well, a proton has a mass of 1 AMU, a neutron has a mass of 1 AMU, an alpha particle, that's a helium. It's got 2 protons, 2 neutrons for a mass of 4, but a beta particle is an electron. And if you remember, electrons are tiny. They're 1/1000th the mass and size of a proton and neutron, and so we get that the beta particle is the lightest type of radiation, a nuclear radiation particle. All right. Hopefully we have a sense of the type of particles now that we can run across when we undergo nuclear radioactive decay. In our next video, we're going to practice doing a little bit more of those balanced reactions. Thank you.